Namaste to everyone. I welcome you all in my YouTube video channel. Today, I will deliver lecture on theory of numbers, lecture number 46, in which I will solve some more problems on order of an integer modulo m. Now we solve a problem. Problem is, let P be a prime divisor of a Fermat's number Fn. Fn equal to 2 to the power 2 to the power n plus 1. So that order of 2 modulo P equal to 2 to the power n plus 1. Now we solve this. Given that P is a prime number such that P divides Fn. Fn is a Fermat's number. This is number 1. That is, Fn equal to 2 to the power 2 to the power n plus 1. This is number 2. Since Fermat's number is an odd integer, therefore from 1 it is clear that P is an odd prime. Therefore, GCD of 2 and P equal to 1. This is number 3. Since from 1 P divides Fn implies that P divides 2 to the power 2 to the power n plus 1 implies that 2 to the power 2 to the power n is congruent to minus 1 modulo P. Squaring we get 2 to the power 2 to the power n whole square is congruent to minus 1 square modulo P, implies that 2 to the power 2 multiplied by 2 to the power n congruent to 1 modulo P, implies that 2 to the power here 1 plus n means n plus 1 is congruent to 1 modulo P. This is number 4. From 3 and 4 we get order of 2 modulo P equal to 2 to the power n plus 1. Here 2 to the power n plus 1. Proved. Now we prove a theorem. Theorem is, if the order of a modulo m is n, then a to the power r is congruent to a to the power s modulo m, double implication, r is congruent to s modulo n. Now we prove this. Given that order of a modulo m equal to n implies that a to the power n is congruent to 1 modulo m. This is number 1, where n be the least positive integer. Now let a to the power r is congruent to a to the power s modulo m, implies that multiplying both sides by a to the power minus s, a to the power r multiply a to the power minus s is congruent to a to the power s multiply a to the power minus s modulo m, implies that a to the power r minus s is congruent to a to the power s minus s, means a to the power 0, that is 1 modulo m. Let this is number 2. From 1 and 2 we get here n be the least positive integer. Here we have r minus s as power of a. Therefore, n divides r minus s, implies that r is congruent to s modulo n. Proved. Conversely, let r is congruent to s modulo n, implies that n divides r minus s, implies that r minus s equal to qn. Q is an integer. Let this is number 3. Raising power q in both sides of one, we get a to the power n to the power q is congruent to 1 to the power q modulo m, implies that a to the power nq is congruent to 1 modulo m, implies that a to the power, using theory, r minus s is congruent to 1 modulo m. Let this is number 4. Multiplying 4 by a to the power s, we get a to the power r minus s into a to the power s is congruent to a to the power s modulo m, implies that a to the power r is congruent to a to the power s modulo m. Proved. Now we prove a theorem. Order of a modulo m equal to n implies that order of a to the power k modulo m equal to n by GCD of n and k, where k is a positive integer. Now we prove this. Given that order of a modulo m equal to n, this is number 1. Therefore, GCD of a and m equal to 1, this is number 2, and a to the power n is congruent to 1 modulo m, where n be the least positive integer. Let this is number 3. Now let k be a positive integer and order of a to the power k modulo m equal to r. Let this is number 4. Implies that a to the power k to the power r is congruent to 1 modulo m, implies that a to the power kr is congruent to 1 modulo m. This is number 5. Let GCD of n and k equal to d, implies that d divides n and d divides k, implies that n equal to n1d and k equal to k1d. n1, k1 are integers. Let this is number 6, this is number 7 and this is number 8. From 6, GCD of n and k equal to d, implies that here n equal to n1d and k equal to k1d equal to d. We may take d outside. D GCD of n1 k1 equal to d implies that GCD of n1 k1 equal to 1. Here we divide d in both sides. Let this is number 9. From 3 and 5, we get here in theory n be the least positive integer. Here kr be the power of a. We get n divides kr implies that n equal to n1d. Here k equal to k1d. Multiply r implies that n1 divides k1r. D cancel. Let this is number 10. Using 9. Here GCD of n1 k1 equal to 1. So from 10 n1 divides r. This is number 11. Now a to the power n to the power k1 equal to a to the power n means n1d to the power k1. This equal to a to the power n1 dk1. dk1 means k. A to the power n1k. Let this is number 12. Now raising power k1 in theory we get a to the power n to the power k1 is congruent to 1 to the power k1 modulo m. Implies that a to the power nk1 is congruent to 1 modulo m. This is number 13. Using 12 we get here a to the power nk1 equal to a to the power n1k. Here we write a to the power n1k is congruent to 1 modulo m. Implies that a to the power k to the power n1 is congruent to 1 modulo m. This is number 14. Since we have assumed that order of a to the power k modulo m equal to r, implies that a to the power k to the power r is congruent to 1 modulo m, where r be the least positive integer. Let this is number 15. From 14 and 15 we get here in 15 r be the least positive integer, and here we have n1 as power of a to the power k. Therefore r divides n1. Let this is number 16. From 11 and 16 we get in 11 n1 divides r, and in 16 r divides n1. Therefore, r equal to n1. Implies that r equal to n1 means n by d. D be the GCD of n and k. That is n by GCD of n and k. And r be the order of a to the power k modulo m, and this is equal to n by GCD of n and k. Proved. Now we solve a problem. Problem is, if a order of a modulo m equal to n, then so that order of a to the power k modulo m equal to n, double implication, GCD of n and k equal to 1. Now we solve this. Let order of a modulo m equal to n. Therefore, GCD of a and m equal to 1, and a to the power n is congruent to 1 modulo m. N be the least positive integer. Let this is number 1, this is number 2, and this is number 3. Let k be a positive integer. Therefore, order of a to the power k modulo m equal to n by GCD of n and k. Here we write n equal to n by GCD of n and k. Implies that GCD of n and k equal to 1. Proved. Conversely, let GCD of n and k equal to 1. Let this is number 4. We know that order of a to the power k modulo m equal to n by GCD of n and k, where n be the order of a modulo m. This equal to n by using 4. Here 1 equal to n. Proved. Now we solve the next problem. Next problem is, so that if GCD of a and m equal to 1 with order of a modulo m equal to st, then order of a to the power t modulo m equal to s. Now we solve this. Given that GCD of a and m equal to 1 and order of a modulo m equal to st. This is number 1, this is number 2. Let t be a positive integer. then order of a to the power t modulo m equal to order of a modulo m by GCD of order of a modulo m and t, and this equal to order of a modulo m equal to st using 2. Here GCD of order of a modulo m is st and t using 2. This equal to st by, here we may take common t, GCD of s and 1 equal to st by t, GCD of s and 1 is 1 equal to s. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.